Hello everyone, this is our fourth week. Let's start some problems from chapter first 12. Some problems. After that we will solve problems from chapter 13 and 14. So let's start from chapter 12. So let's consider problem 36 or 46. We are given, so it's given long hollow this cylindrical conductor, right? So we are given this one. So here we have conductor. Okay. So inner radius is given R1, and also outer radius is given R2. So R1 is 3 centimeters, R2 is 5 centimeters, and the current 50 amperes current distributed uniformly over the cross section follows into the page. So current in this page, right? So let's just put it here. Here we have current going in that direction. So I equals to 10 amperes. 10 amperes. Oh, sorry, 50 amperes. 50 amperes calculates the magnetic field at, so B is not known, so we need to find at R equals to 2 centimeters, R equals to 4 centimeters, and see R equals to 6 centimeters. So first let's start with A. So R equals to 2 centimeters, it means that it's smaller than R1 in a radius. Then we need to calculate magnetic field in this empty space, almost inside this hollow cylindrical conductor. So first thing we need to do is to apply the Ampere's law, right? P dl equals to mu0 I enclosed using Ampere's law. So let's draw the Ampere's loops inside this. So here this is Ampere's law, Ampere's loop for part A, right? So we can see that there is no current, right, enclosed in this Ampere's loop. There is no current into the page or out of the page, so it's 0. So for part A it's 0. Part B, R equals to 4 centimeters. We know that 4 centimeters is inside R1 and R2. So let's put the Ampere's loop inside this conductor. So this part is R now. How we will calculate? So for all these Ampere's loops, we know that it's cylindrically symmetric because current going into this direction. So we will have anyway B 2 pi R, and this is also actually automatic. I hope that you know it like immediately. So mu0 I enclosed. So what I enclosed here? First we need to find, in order to find this quantity, we have to know, since current is distributed in this cross section uniformly, we can actually find first current density, right? Density equals to current, initial current I0, right? I0 divided by this whole area, this surface area, which is equals to, here since we have inside this, it's empty, right? We need to give, I'm sure that P, so this is outer radius is R2 squared minus R1 squared, right? Actually, if it were like a whole closed solid, then it would be like surface area would be PA squared. But in our case, it's inside it's empty, right? That's why I substituted this value. So since we know the current density and its current is uniformly distributed over the surface, we can easily find this enclosed current. So I enclosed for part B equals to G multiplied by okay, J multiplied by PR squared, right? This, but we know that for PR squared is for this surface area is for solid angle. Again, we have to okay, let me denote it as R prime. We have to do the same trick like this, right? So it's first we substitute G I0 over P R2 squared minus R1 squared multiplied by P. So R equals to, here we have inside it's R, so R squared minus R1 squared. So makes sense, right? We are calculating this one in this direction. Equals to I0 R squared minus R1 squared divided by R2 squared minus R1 squared. So all we need to do is substitute into this Ampere's law, or how it's called, this equals to nu 0 I enclosed over 2pr. R is over this 4 centimeters. Let's substitute everything. 2 pi r I0 R squared minus R1 squared R2 squared minus R1 squared. So I will stop and I will calculate all this after substituting. So here I substituted all the values, given values for pi. So I obtained this 1.1 10 to the minus 4 Tesla. So what about R equals to 6 centimeter, which is outside this conductor, right? If we put this Ampere's loop, then we will again, in that case we will have just, okay, P2 pi R multiply equals to nu 0 I enclosed. In that case I enclosed equals to total current, right? Since this Ampere's loop contains all these currents. So we have P equals to nu 0 I running in 2 pi R. Actually I've just calculated it and substituted all the results into here, 6 centimeter. I obtained 1.7 minus 4. Now next let's consider problem 48. We are given this cable, long cable. Actually, okay, let's put it like this, and after that we are also given like another cable, like, let me actually draw this. So we have like cable, we can actually put in, we can suppose that the inside is empty, and we are given these 3 values, R1, and this radius R2, and this outer radius R3. So current first goes, okay, let's draw properly, right? So here we have cable, long cable. Current going inside this cable in this direction, and outside in this direction. So we need to find magnetic fields in regions A, R1 inside this, in part B, R2, R1 and R2. So inside this one, this empty space, and the C, R3, R2. I think I made the reverse. R2 bigger than R, and R bigger than R1, R3 bigger than R in this direction, which is here, and finally we have to find outside this. So to solve part A, let's draw the, as usual, Ampere's loop inside this, right? So inside this we have okay, and here we have another. For example, if we put Ampere's law here, Ampere's law here, Ampere's law outside this, everywhere we will have 2 pi r. Okay, let's write p dl, since it's cylindrical symmetric, right? 2 pi r equals to nu 0 I enclosed for all the cases. So let's substitute for a. So 2 pi here beta, 2 pi r beta equal b magnetic field equals to nu 0 I enclosed. But as usual, we know that in order to find the current enclosed here, since current also in this problem also uniformly distributed, we can first find the current density inside this thing. So current density equals to I0 initial current, right? I0 divided by PR. So here we have PR1 square, right? So total current enclosed in that direction equals to first current density multiplied by P, these are inside this small r, then PR squared equals to I0 PR1 squared multiplied by PR squared. Hence I enclosed equals to I0 R squared over R1 squared. So let's substitute here. 2 pi r beta b equals to nu 0 r square r1 square. So we have here cancels, and from here magnetic field is equals to nu 0 I0 divided by here r 2 pi r1 squared. So let me substitute everything. Actually we are not given, so we find it. We are not given quantities. We have to find just formulas in part B. So in part B we have R in this space, right? So here total current is enclosed in this total current. So it's just 2 pi R B equals to nu 0 I. That's all. B equals to nu 0 I rolling in 2 pi r. So we found it in part C. So current look here, part C, we need to find magnitude, but here is some complication, because in this loop current going into the page, but in this Ampere's law current going out of the loop, right? So we have to find the difference between these enclosed, right? So in part C, so R3 bigger than R3 R2, 2 pi RB equals to nu 0 I enclosed. Here I enclosed equals to first this total current into the page, which is, you know, current going this total enclosed this one. Okay, no, I'm talking about this thing, right? So it's current minus nu 0 I minus current. So here we will also find similar to the previous problem, right here. So it's in this one it's R2, and this is whole thing R3 inside R, right? So it's current density. First find current density out of this thing, P, so current divided by P R3 square minus R2 square. So R2 square, R3 square minus R2 square. Yes, we found it. And current enclosed in that direction equals to G P R square. But again, it's inside this, it's empty, right? So it's not just R square minus R2 square. So I enclosed equals to G equals to I0 over P R3 squared minus R2 squared multiplied by this thing P R squared minus R2 squared. So let's write it. R squared minus R2 squared over R3 squared minus R2 squared. So we found it. We can substitute actually this value into here, right? I enclosed this thing because we have currents, this current also going into the page, and we've just calculated this, which is out of the page. That's why I put this one into this. So let's find B. B equals to mu 0 I. So this is I0, right? I0 minus I0 R squared minus R2 squared over R3 squared minus R2 squared divided by 2 pi R. That's it. We found it also. And finally, in part D, we have to find magnetic field right here. So this is automatically, we can see that current enclosed is 0, right? Because this is into the page, and this current also whole current out of the page. So this net current equals to 0. So P equals to 0. So we found it. Now let's consider again another problem, 87, which is actually easy problem. Here we are given toroid. So here we have it's evenly spaced as in the problem statement, right? We are given inner axis, which is A, and the outer up to here, which is B. So magnetic field inside the torus we need to find. So torus here we have actually its shape, cross-sectional shape, it's rectangular, it's written. So we are given a torus of rectangular cross-section with inner radius A and outer radius B. So also n turns of an insulated thin wire are wound evenly on the torus, tightly all around the torus, and connected to the battery, producing a steady current I in the wire. Assume that the current on the top and the bottom surfaces inside the figure is radial. So and the current on the inner and the outer radius surfaces is vertical. Find the magnetic field inside the torus as a function of radial distance from the axis. So even though this problem statement is somehow how it's called complicated, actually this is the same as for example, let's put R here and find magnetic field here. So if we consider again as in your book, like so here we have cross current going out of the page, so it's evenly spaced, right? Current going here into the page. So actually here we have Ampere's loop, and the current goes only into the page here, right? Into the page. So n we are given n, so 2 pi r. So we are given big R, right? B equals to n nu I. That's all. We found it. N nu I over 2 pi r. This is actually the similar as in the lecture, I mean in your book, but the main point in this problem is that even though this our torus, cross-sectional torus is, I mean cross-section of this torus is rectangular, we will anyway get the same answer as even though it's with the case of circular torus. So it doesn't matter, right? Now let's move to the next chapter, chapter 14. Oh, sorry, chapter 13, and we will consider some problems. So let me stop.